last time I just started with some generalities, and fortunately, otherwise, they have to continue a little bit more with generalities, and I had to tell you how this whole field developed historically and what are the motivations. So the first statement I made last time was that, I mean, in my personal opinion, the way quantum mechanics is taught, as I have taught in the classes, is somehow misguided. It is very mysterious. It was very mysterious when I first read, say, Messiah or somebody like that. And I think it should also be very mysterious because out of nowhere, a wave function, a Hilbert space appears, which has no trace in classical physics. Although at some point one says that classical physics is some limiting form of quantum physics, but you don't know why, because you don't see any Hilbert spaces in classical physics. So the motivation was that to remind you that already I had felt, say, let us say, since I got acquainted with this field, I had felt that this is not the way to teach physics, quantum physics at all. Okay? Already in the, due to, I think, very likely, if I were to trace the history, it goes back already to Hermann Weyl, who already recognized that somehow, for example, the things like dimensions of space-time are encoded in Hamiltonian dynamics, in the dynamics we do in quantum theory, and he had written down very general formulae for us how to deduce the dimensions of space-time from the spectral properties of the Dirac of the, well, he wrote it down for the elliptic operator, for the Laplacian, and he showed an asymptotic formula which encoded from the analysis of the spectral properties, the growth of the eigenvalues as you keep increasing the eigenvalues, how you can deduce the dimension on which this operator is written. This worked out, Hermann Weyl, I think, goes back to the late 30s, if I remember correctly. Okay. And soon afterwards, the Gelfand school, Gelfand, Naimark, and other people realized that there was a form, they first must have realized, because they knew quantum mechanics, they had contributed to quantum mechanics, that in quantum theory, neither in classical nor in quantum theory do we measure points, okay, or we measure dimension. The data, the raw data that we get from measurements are not things like points, but some algebras. So somehow I think they got involved in this issue of how to deduce properties of manifolds in space-time from data coming from experiments, and they proved this very fundamental theorem, which is usually called as the. They had realized that what we observe are certain algebras, and they proceeded at that point, I don't know, reviewing last week, to look at what happens if the algebra is the algebra that comes from classical mechanics. So from phase space of classical mechanics, which happens to have two distinct properties, which I had mentioned last time. So how do I move it up and down? So they had already worried about what happens in classical physics. I don't know whether that was a specific motivation at that time, but they started with classical physics and realized that in classical physics, or we can reformulate what they had taught as the statement that in classical physics, what we are observing are functions on the phase space. So we are just getting some functions. We don't even know what the phase space structure is. The algebras, so these are algebras of functions which have some properties like multiplication properties, and they Poisson bracket. Yeah. So there are certain multiplication properties. So if I take two, so a function is something which normally in phase space gives a value at the point of the phase space. So naturally it comes from a multiplication, because you can multiply values of the functions which are complex numbers. well, actually, classical mechanics is real, but there is complexify them. Then you can say that the product of two functions, F1 and F2, is defined intrinsically by saying that if the value of the product at the point QP is the value is the values of F1 and F2 are the targets. That is F1 at QP times F2 at QP. This is naturally defined, but at, the intrinsic property we want here is a statement that this kind of product is commutative. So if we switch the positions of F2 and F1, the value that you get does not change. Okay? So it is a commutative algebra, and it has a new property as well, namely the property that you can take Poisson brackets. So so in addition, this is the property that there's an additional structure, which is not only an algebraic structure, namely you can take Poisson brackets, and it is close to taking Poisson brackets. And it is preferable for certainly for mathematical analysis, and we lose nothing, to imagine these functions as complex values. They realized this, then they proceeded to investigate such functions. Okay. This kind of algebra is quite abstractly. So, but in physics, they have one more additional structure, namely, if you have so these functions that you are the correct way, good way to think for us about these functions are the objects which the experimentalist measures. In classical mechanics, it could be a charge density, for example, or it could even be a scattering amplitude. So they are the ones which your lab is going to measure at the end of the game. But the objective system, which may be coming from an LHC ring, are given by states. So the states of the algebra, which very often is written using wave functions, which I'll come to later, are the ones which is describing for you the abstract system which the lab is testing. Okay? So neither of this separation is not very sharp, and neither of them are accessible to anybody except mathematical equations. But the thing that get out, the table that the experimentalist prepare is the value of the state on the algebra, which is the outcome of the experiment. Okay? So what we are measuring is what I have called here omega f. So the stuff that comes out of the lab is value of the state on the property that we are measuring, which is omega of f, and we want to think of this omega as a probability distribution on these functions. So it must have two properties because it is a probability. One is that it must, on the identity function, which is unit, is constant on the entire phase space. So this algebra has something called the unity, which at all points, which is unity in the algebraic sense, that you multiply anything with one, nothing happens. And experimentally, we mean that it is a function with equal values at all points of phase space. We want this omega to be 1. Okay? So this is the total probability, and that is a normalization condition on the omega. Okay? And secondly, because it's a probability density, it should be positive. That is, you take a positive function, for example, a star f, which is necessarily positive, this omega should be positive. So Gelfand and Naimark started investigating this situation. So we have a commutative algebra with this structure, and then they realized that this kind of algebra has some additional properties.
It's a nice question, but so imposing this condition of identity is going to work. Does it mean to say that we cannot deal with open systems in this way?
We can do what?
We cannot deal with open systems using this form.
No. So we can, of course, but you can assume, well, you can certainly consider cases where only the norm of m this is not 1 but less than 1. Okay? But normally, natural thing to do is not that, not to do this normalization, but consider what Subhashish what they call POVs, that is positive operator value measures, which will be essentially an open system because you are coupling it to something else. Okay? But the normalization is maintained. But you can also consider developed cases where this omega is not normalized in this fashion. There are even cases where you forget about omega normalization altogether, but only retain the positivity, and then you get not states but what they call weights in the mass literature, and that can also be applied to get physical consequences. So all these cases can be covered with increasing levels of sophistication and difficulty. So what I want to emphasize, so I am writing omega with a normal language by taking some density matrix F and integrating over the volume. F is like a density matrix. So is it giving you not omega? Yeah, omega is like omega QP is like a density matrix. F is what we are observing. And I'm writing a formula, imagine if it's actually a function given to you on a phase space, but that's not necessary. There are theorems that you can write like this. So this is what you are given. This is our experimental setup. And the Gelman-Neumann theorem, which I think is extraordinary, is a statement that if you give me this algebra with this omega, with this property, then you can recover the original phase space to a large extent. Large extent means you can recover this topology. That was the first, I would say, not essentially the first. What I know is that after Hermann Weyl, this is the first instance where I saw somebody focusing on problems which are epistemologically interesting physics. Somebody may say this will not tell me the Hadron atom spectrum, okay? But I think we have other things like it's beyond computing Hadron atom spectrum. We want to know what is happening. So this is, I think, this is probably at that time, Göttingen and Stalingrad and so on must be boiling with ideas. So here comes, this was the start of the ideas. There is it. Okay. But there is another point I should mention, that when you write an algebra like this, yeah, I call this, because it is a commutative algebra, I call it as AC. Okay. So I call this C. C is to denote that it is a commutative algebra. So what I have told you is that in this commutative algebra, with the state given to you, you can recover a certain basic property of the space-time or the spatial slice, or let's say in this case, the phase space. You can recover much of it, certain fundamental characteristics of the phase space. You will not recover all the characteristics, but you can recover certain fundamental characteristics of the phase space without further knowledge. But there is one more ingredient which is going to play great confusion with quantum theory, and that is the fact that this kind of algebra has a norm. Okay? Norm is that you have to tell how to measure things, which is not very so. We cannot say I am very far from Sanatan. That is a colloquial way of saying it. I had to give you a measurement distance. In this case, we may tell how many kilometers he is from me, for example. Here, in mathematical thing, you need a norm. What replaces that notion is a norm. And there's a natural norm. This is an observation by Gelfa and Neumann. And the norm is given by saying the following. The norm is given by obtained by saying the following. Norm of F is you take all the states which are available to you on the algebra, evaluate it on the function. I should say, when I write supremo or omega, there should have been a modular symbol on omega over there. You take the modular symbol, it's a complex number, and you take its maximum over all the available omega. Omega is normalized so that this omega cannot grow arbitrarily because on 1 it is 1. So you cannot multiply it by 2 or anything like that. So there is a maximum, and you take the supremum, and the supremum of this is what is called the norm. Okay? There are various ways of computing it. If it is an operator, there is another formula which is very simple to calculate actually. Say for n by n matrices, I'll come to that later. Sorry?
What set does omega belong?
Omega is a normalized positive, is normalized. So omega at 1 is 1. Okay. So if I say that if I ask, if I take supremum of all omega, the omega can grow arbitrarily large. So they can multiply omega by 200. Then this supremum has no meaning.
It's normalized, but there's some distribution, right? What
in the classical mechanics, there is a theory, probability theory. Okay? So Kolmogorov and so on, there is a probability theory. Then one knows that these omegas, the states or the thing which is you are integrating belong to what I call a sigma algebra. Okay? there is a, if you take a book on probability theory or look in the prices that Bharadhan got, you find immediately the definition of the sigma algebra, but I don't want to go into that. It doesn't play any essential role here, except that it cannot grow arbitrarily. Yes.
Then, system mechanics data saved like by Q and P, this means that
Omega is so if you want, you can take it to be a smooth positive function, like a density matrix. You can take it to be a smooth positive function on phase space, which is normalized to 1.
so what is the normalized?
That its value or the identity function is 1. The average value is, if you take the average of identity function on all probability. So omega is the probability, it says the probability gives the probability of finding an observable in some part of the phase space, where omega is, you are integrating omega. Okay? So probability of finding it anywhere in phase space could be 1. That is the idea. Okay? So the normalization condition is that of a probability measure. Like a density matrix in quantum mechanics, where trace of rho is 1. It's the exact correspondence of that. Okay? And if you want to be a bit more sophisticated, this f need not even be a continuous function. It can be what they call Lebesgue squaring, Lebesgue function, some Lebesgue measurable function. So you can loosen this requirement on what this omega is progressively, and people doing this, but with rare events and so on, okay, will be like Bharadhan who got the Nobel Prize. Okay? They will be concerned about those things, but we need not be worried about such technicalities. Okay? The kind of thing I am going to say is not relying on technicality, quite loose. You can do many things. Okay? Don't bothering about that. You won't make mistakes. Okay? Let's say it is robust. That's the language that we use. Okay? So there should have been a modulus, and because this is the way I have defined the norm, there is a basic property that comes out, namely the maximum of in this norm a star f. So the star operation f is a complex valued function. I have taken it to be complex value function. So a star means, if you write it as a function on the phase space, a star means a star at the point QP is f of QP bar. F of QP is a complex number. I can take a complex conjugate of that, and that is what that will define for you what is F star. Okay? So F star is well defined intrinsically. You don't need the complex numbers. It's a star operation, which is a which complex conjugates all the coefficient functions, which are complex numbers, and it also there's an intrinsic conjugation which is defined on the say the basis of the algebra. So the basic property we want to be focused on is the norm of F star F is norm of F squared. Okay? This may look like an innocent property, okay? But it is not. This is the property which defines what is meant by C star norm. This is what defines C star algebra. Okay? This equation is what defines the C star algebra. It happens that this is fulfilled by essentially all matrix algebras, where the norm is given by the modulus of the largest eigenvalue for a Hermitian matrix, is fulfilled by this. They fulfill this equation, and for many reasons, this is very natural to retain because it gives you many physically interesting results. For example, this kind of equation is what relies eventually in quantum field theory to give you the spin statistics theorem, or this thermal states of quantum fields. This is the equation that this stuff on Tomita Takesaki theory. It is this equation which is underlying the whole calculation. So it is not such an innocent equation that we are writing. Okay? So I want to know what happens. Okay. Now I want to do quantum mechanics. So I want to see what happens if AC is not commutative. Okay. So I told you already how we deduce manifolds from this data briefly. But there's one point I want to emphasize. If you give me this algebra and this star operation, if I look at exponential IF, where if we say an element of the algebra, I can imagine defining exponential IF as a power series in this expression. Okay? And you can show that it converges. Okay? The power series converges in the algebra norm. Okay? Now, the main property of this exponential IF is that it is unitary. Because if I take the star, okay, the star will take for a real function f. If I take the star, it will go to the inverse. Right? The I will change the sign and f will go to the S star will be f, so it will go to the inverse. So the star operation takes u to u inverse. So you would say that u is unitary. Now, if I have a unitary map like this, let me see if I can find. Yes, I have it. So there is one property in the commutative case. Take any element of the algebra. So it's any function in the algebra. If in quantum mechanics, you know that if you make unitary transformations, the algebra remains the same, isomorphic. It will permute the elements of the algebra, but no algebraic relation will be changed. For example, if I take angular momentum algebra and I conjugate all the angular momenta by rotations, nothing will happen because algebraic structure. Likewise here too. But here something more happens. If I conjugate an element A of this commutative algebra with U, it doesn't change at all. Okay? It changes U star is U. Okay? Because it is commutative. Okay? U passes right through A and nothing happens. This is a characteristic of commutative algebras, or I would say of classical mechanics. And you will see that this relation causes a lot of difficulties when we go into quantum theory. Okay? And from the extent I can understand, this is the basic result. The fact that this equation is no longer true in quantum theory is that the basic fact which underlies the fact that measurement theory is extremely complicated in quantum theory. I'll come to that immediately. So here I have made something about some rhetorical remark about whether. So I will assume that measurement problem does not exist in classical theory, but I had doubts on that. We can discuss it. Govindarajan made some suggestions, but I was thinking about it. I don't know. I think we can raise measurement problems in quantum theory, in classical theory. But let me put them aside. Assume that I know at some point you put a cutoff and I will say, I know, here on I know the answer. Let me say that. For example, we claim that we know natural numbers. Do we? Do we know what is an irrational number? That requires a lot of things to do. But at some point we put a cutoff and say, I know it. I know how to calculate. So let me put a cutoff here and go on to quantum theory. Okay. So when I go into quantum theory, let me point out right away. Somebody was asking me this, that the way we are taught, for example, take position. Where do we start the quantum theory? For example, one of the primary things we start with is if I'm doing, say, hydrogen atom in 3 dimensions, we have position of, let's say, on a line. We are doing quantum mechanics or particle on a line. We have position operators x and p in classical mechanics, and we take hats on these operators, which are the corresponding quantum operator, and we write this equation x hat with p hat is I h bar times 1, and claim that this is the basic of quantum mechanics. But this equation cannot be right. Something is wrong. Because if I take the trace of both, this is something many people know. But if you take the trace, you get immediate contradiction. The trace of 1 is infinity, because the Hilbert space is infinite dimensional. But the trace of a commutator is 0. We are taught that from mechanics, from finite dimensional matrix algebra. So this equation cannot be right, as it written. Okay? So what is happening? Okay? So I will not go delve into what go from notes now, what goes wrong, okay? But I will not go into that. Okay? Maybe there is interest, we can study unbounded operators and bounded, how the domains of operators is solved. Again, it is at least the people involved in our group think that this has become important in many contexts. For example, for the X states in quantum mechanics and hardness matter physics, this kind of problem comes up. But for the moment, let me say that there is a problem here. So there is something wrong with this equation. It may not matter for most purposes, but can matter for some other purposes. So let me keep that aside. I can see Sitendra looking at it. I don't know why. Yeah.
Without noticing,
No. I mean, at some point in your game, somebody comes and says, "What is this? Is in matrix P has the matrix? I take comment at a take simplicity of the trace is zero, but trace of one is infinite. What am I doing? Okay. Okay. So something wrong. So how do I get uncertainty principle from a wrong equation? What does it make any sense? Okay. This kind of manipulation is also done. Some of you may know, but the time Hamiltonian uncertainty principle. Time. That is the most horrendous equation you can find because time operator is not even an operator in quantum theory. What is the meaning of that equation? And somebody here was asking about time of arrival problem in condensed matter systems, and people trying to write such equations. Okay? And apparently, that is of interest in, for example, in mesoscopic systems. Okay? Kumar was asking one time, we were discussing. But the interpretation of those equations requires some subtlety. You can't just write T with H equal to IH bar. Doesn't make sense. And use it for computing lifetimes. Well, the answer may be right, but like cooking, my cooking, the answer may be right, but intermediate steps are absolutely horrible. So I don't know what is happening. Okay. So what do I do? Okay. So you end up by taking trace that everything is infinite. So let us not do with that. The problem can be resolved if I work with the unitaries. What do I mean by unitaries? It is possible to excite this excite and pay hat are not diagonalizable operators. There are no eigenstates for excite, not other eigenstates for pay hat, except in the Dirac sense. They are not vectors in the Hilbert space. So it is better to work with the corresponding unitaries, which can be defined in a good way. And you look at U of x hat, which is exponential I x hat, which is at least formally unitary, likewise U of p hat, and look at their algebra.
you say that they're not eigenstates P will not be normalizable.
Yes, so they are not in the Hilbert space. And Hilbert space vectors must all be normalizable because they give you allegedly probability densities according to Bond's interpretation. Then you will get infinity. So as it stands, it is not in the Hilbert space. If you want to interpret them in some sense, and if you are really interested, there is some other junk, Gelfand triple and so on. But let me see, this is like the octopus. These arms go in many ways, which normal teaching doesn't train people. So how did we learn? By living long and reading books. This is no unique, no quick way. So we talk about it and other people know. There is a way to handle that issue, the fact that it is not normalizable. But then you get domains and the distributions on domains. Something called Gelfand triple, which manages that problem. But let me put it aside. So yes, it is not normalizable. So it cannot be a wave function. If somebody says it is a wave function, it is simply wrong. Okay? Except in a colloquial sense. Okay. So I work with the unitaries, and then you look at the algebra of the unitaries. Yeah. Yeah. You look at the look at the algebra of the unitaries, and you find from the combination relation you are given that that equation corresponds to this equation. Okay. You invert it, you get an exponential minus I h bar. Okay. This equation happens to be perfectly well defined. Okay. Because you are working with unitary operators, it happens to be perfectly well defined, and you can make it into an algebra. Take all complex linear combinations of here there are only x and p, but you take all complex linear combinations of these two operators, all their polynomials. Yes. This is the what is called Baker Campbell Hausdorff. That's why I'm telling. Exponential A, exponential B. This is what is it called? Baker-Campbell-Hausdorff formula. Is exponential B, exponential A times exponential of minus 1/2 of A commutative with B. Okay. This is used in, I think many people, you know. Baker-Campbell is called BCH formula. I think people, I can derive it if you want next time. It's trivial. Okay. Okay, you can take this equation. This vector side is equal to exponential u of p hat, u of exponential I, then conjugate that p hat with exponential I s hat. That is the same thing because the u's cancel out. And that translates p hat by certain amount. That amount is given by the coefficient of x hat. This IH bar. So you can just get a C number, you can pull it out and you get
These are nothing that computed.
it is coming from there.
X and P.
X and P.
But you said that is wrong.
That is wrong, but this equation is right.
Why? You use the wrong equation to get something.
That is what we do all the time in physics. No, I mean, you abandon that. One's idea was to abandon the first equation and start from here. Okay? So, this is enough to derive all the consequences of the first equation, including the uncertainty principle. And the operations you are doing are well defined and you don't get contradictions. So you took the algebra, so you take u of x hat, u of p hat, all their polynomials with complex coefficients, and that's a perfectly well-defined algebra, and it is usually called as a Weil algebra. Okay? So it is preferable to work with Weil algebra because it is well-defined. The first one, you can work with it, not that operation equation, but some other algebra associated to it, and that is a very complicated algebra of all bounded operators on a Hilbert space. That is quite huge and very difficult. Very difficult to have. You can't diagonalize operators. Well, all bounded and unbounded operators on a Hilbert space, in most of them you cannot even diagonalize. So it is very difficult to handle this, and it was so people, for example, Weidmann formulation uses that. And it is very difficult to handle. Okay? Whereas if you look at unitaries, the kind of problem that Weidmann formulation faces go away. Okay? So it is much easier to handle without getting into heavy analysis. Okay.
Some people with the fact that you're going to ultimately deal with probabilities both in classical as well as quantum.
Say again.
But some people with the fact that in classical as well as quantum, you have to deal with probability of certain quantities. And therefore, the fact that probability will come with a norm is probably one of the universities.
Operators will come with a norm. Behave as S.
Something like you don't have to have something like a rare.
A rare representation, I'll come to that. Okay, I'll come to that. That's a good question, but the next PDF has that addresses that issue. So this algebra generated by u of x hat and u of p hat as the generating elements of the algebra is what is normally called as the Weil algebra. So here I have written down this algebraic structure. So you take linear combinations of all these unitaries with complex coefficients. Unitaries also taking all possible products and all finitely many products of u's and p's in whatever the order is. Take their complex combinations with coefficients which are complex numbers, and this happens to be also an algebra. You can multiply two of them, obviously, because I can multiply two u's, and I have to put a norm here to imitate what is happening in classical mechanics. And the norm again is, so you have this algebra, then you can, because it is an algebra, I can define the state on this algebra. Exactly as I did earlier, omega. So omega is a positive, omega acting on so omega is telling the system that you are checking and acting on an observable. Could be charge density or it could be something energy, exponential of the energy. So anything that is properly defined, you can apply this omega to get a complex number, and this omega is a state. So omega will give on positive operators positive numbers. What is the positive operator? So positive operator will be an operator of the form. Uh, yeah, A star A. Suppose A is an element of this algebra. The positive operator will be A star A. So it will be like A dagger A. A dagger A has all eigenvalues positive. Here it is more abstractly written as A star A because I have not told you what's dagger, which I will do next time. So I want to see. Yeah, and it's again normalized to 1. Omega at 1 is 1. Okay. So here I have written down omega at 1. So the unit operator is simply the unity in this whole algebra, which multiplying anything gives 1. It gives back that element is 1, and we want omega to be 1 on that element. Okay. So it's again a probability distribution. Omega is a probability distribution on a non-commutative algebra. Okay. So the difference from the point of view of algebraic quantum field theory is the basic difference is classical theory is on a probability theory of a classical algebra, and the quantum theory is become probability theory on a non-commutative algebra. Okay. This is the basic difference. This is what causes all the differences between the two systems. So this little thing simply explodes into a lot of differences between the two systems. Okay. So you see how it happens. So what is the norm? These are operators. So the operator norm is the norm here is defined in the same way as we define the norm on the commutative algebra. Okay. Take omega, all omega, take the supremum or the value of omega on any element A, take the modulus and take the maximum, and that is the norm of A. And the remarkable thing is again that omega of A star A is omega of A times. So omega of A star is positive, of course. And again, the remarkable thing is omega of A star A is omega of A modulus squared. The norm of A star A is equal to norm of A squared. Okay. This is a property which also the classical mechanics enjoys, and we will see that this is very central to the entire analysis. Okay. So this is what controls the probability theory in this situation. Now, let me see whether I understand.
But
Hmm.
you had a equation for omega f.
Yeah.
As an integral.
Hmm.
What is the equation for omega f?
So yes, I understand. So here, that kind of formula to get it, we have to the next lecture, given this omega, there's a good question, and the algebra, I will be able to construct a Hilbert space, depending only on this data, Hilbert space of the garden variety, on which these A's operate as linear operators acting on that Hilbert space. So Hilbert space will be an emergent property, not intrinsic. It's simply consequence of definitions that we are dealing with. Okay. And it will emerge from that equation. And what is called the norm of A, suppose A is a self-adjoint operator, will turn out to be the maximum eigenvalue of A. So take the eigenvalue, which is the maximum modulus, that will turn out to be the norm. Okay. So the norm of this that operator will turn out to be, you take omega, you have got I'll consider Hilbert space from this data. Okay. Namely, just give me a data. This is the GNS construction. The data only tells me the probability omega, this probability function omega, and the algebra. Okay. The algebra may be the algebra coming from QCD, for example, or it could be from some other theory. And I'm given this omega, but nothing more. What Gelfand and co, Gelfand and Reimer found out, and then Siegel also found out, is that from here you can consider the Hilbert space. Then this operators, these elements A of the algebra will become operators on this Hilbert space. The star operation will be Hermitian conjugation on this Hilbert space. And if you have a self-adjoint operator on the Hilbert space, it can be diagonalized. You will not get into the problem of position operators and so on. And take the eigenvalue with the maximum modulus, that is the norm. Okay. So if you, what does it mean in matrices? Take any matrix, group n by n matrix, find all its eigenvalues. Okay. maybe it is not diagonalizable, like it may be upper triangle, whatever it is. But if you take that matrix M, compute M star M, that is certainly Hermitian. Find the maximum eigenvalue of that. It will be some mod lambda square. Then the norm of the original M is modulus of lambda. Okay. That is what it is. So I can calculate it in all finite dimensions. I can also calculate it in infinite dimensions if I have enough strength, but it exists.
So A is act on something.
Later on, next talk. Yes.
So your capital A, the algebra, is what you obtain using that unitary operators.
Yes.
Now, okay, now the state is functional on this algebra.
Yes.
To complex.
Yes. But of course, I started from the quantum mechanical example, tell you where it is coming from. But now I don't have to do anything like that. I will take a C-star algebra, which is norm, and I state on it, and I'll make a quantum theory.
Now it's arbitrary algebra.
Arbitrary, you took your quantum field theory, people will not even tell you that it is coming from a quantum field. It is abstractly defined with certain properties. The major extra property they will put in is causality, which I think is very reasonable.
And this norm is the element of the algebra, right? That
Norm is not, it's a complex number.
So you talk when you say we're talking about the norm, we're talking about the norm of the operators in the algebra.
In the algebra, of course. Omega has no norm. It is just the omega is normalized positive linear functional on the algebra. So if somebody talks to you about a state on an algebra, what they mean is a positive linear functional on the algebra, which is normalized.
Okay.
And it's a linear functional. That is omega on alpha A plus beta B is alpha times omega A plus beta B.
Yeah.
And it preserves the star. Omega A star is omega A bar. Okay. So natural properties, that is what, say, Sundar will talk about. And the generalization, which also is physically important, is what are called weights, where you drop the condition that omega at 1 is 1. Okay. So it may be omega at 1 may be 0. So it is not a probability, but it may still have positivity properties, and that plays also a role in many of these issues. I mean, not maths, physical issue. And I hope there is time to convince you that this is not idle talk. I will try to show it.
The omega is like that.
No. So let me say again, the culture of this whole field is to avoid Lagrangians and actions completely.
Why I say that when a function you can evaluate action with the number. Now what you are saying is that given a function or operator A, we have omega evaluating the complex number or that is the another way.
Okay. So if you want that language, the functional integral that once write down, assuming it is well defined in the Euclidean space, is defining a state on your algebra. How? It is a state of the algebra. What are the functions? The functions could be some correlation function. So you've got fields, phi of x1, phi of x2, or Wilson lines. So Wilson lines will generate an algebra, assuming everything is okay. And what is the omega on that? You take a Wilson line, take the expectation value of the Wilson line in the action, and that is a complex number. That is a definition of a state of the algebra. So this the action in the Euclidean space can be thought of as defining a state on the algebra, namely those elements which give you, of whose expectation values you are looking. Okay, there comes the problem that you need normalization to make sense of the positivity condition. I keep saying the it is important to have this reflection positivity, which people don't can give you trouble. For example, this theta vacuum gives you trouble because there is an I there. So the reflection positivity can give you trouble in this analysis. So let me go to the measurement problem. So this is the quantum theory in its basics is an analog of non-commutative probability theory. You can think of it most straightforward way as a non-commutative probability theory. There is a whole mathematical community which discusses non-commutative probability theory, led by the Romanians, in particular somebody called Voiculescu. There is a whole, and our own friends in Delhi, I forget the name. He used to come here, who is in ISI in Delhi. Parthasari, K.R. Parthasari, and also people in Hyderabad used to do that. And they are very sophisticated. There is a non-commutative probability theory, and there is a definition of entropy and all those things. They have got taken their own route, and it is coming back, as is the case, through matrix models back into physics.
Why don't you return one that is the A is K square? Because in the classical case, it is something.
You prove, I mean, the norm of omega of A in the non-commutative case is defined by the top equation. In the non-commutative case also. Okay. Take all states on the algebra. This algebra operators I write down. Take omega on this algebra and take modulus of omega of A, and for any A, and take the maximum on all possible omegas, normalize to 1 on your identity. It has a maximum that you can show. Okay. In fact, it is unique. There is only one maximum. This is a theorem, again, you can prove quite easily. And that is called norm of A. Okay. Let me call, that's what Kelfan I must take. Take it as a norm of A. Okay. Then one proves that A star A is a star algebra. Take A star A, take its norm to check that it is mod A squared. Okay. Now, it's proved. And you can, as an exercise, go home and show that if you take n by n matrices, which are Hermitian, take its maximum eigenvalue. Okay. So it might have positive or negative eigenvalues. Take the eigenvalue with the maximum modulus. Okay. Take another one with the maximum modulus. Take the multiplication and look at the maximum modulus of the product. You'll find that it is a product of the maximum modulus. It will fulfill this equation. No. Once I give you the norm as maximum, so you take the function, what am I doing? I'm taking the function on a line, normal test, and taking the maximum modulus of the, evaluate it all points on the line, and find the point where its modulus is largest. If I define that as the norm of the function, and you take f bar f, and look at its maximum, clearly it is going to be equal to mod of f squared. Okay. It's almost obvious. Here it is not so obvious. Okay. You have to do some jugglery with matrix, finite dimensional matrix algebra in spectral theory. Huh?
It's a property of the definition of the norm.
Yes, intrinsic property of the definition of the norm. Okay. It is there. Okay. And you can challenge, why am I adapting this norm? Here, can I relax this norm? This I don't know. Okay. What I do know is that if it is relaxed, many results, at least in algebraic quantum theory, will be adversely affected. But we can say, who cares? But it will also adversely affect things like their proof of finite statistics, causality, the fact that you get this thermostates for local algebras that our friend Ed Witten and Longo and Chandrasekharan are talking about the DC space. They will be gone. You can't prove that. Okay. So there are a number of results of interest for us, which seem to be of relevance to physics. If they are not relevant, one should abandon this. Okay. There is no reason to go on hanging on. Right? Yeah.
Sure. So can I ask, what are these definitions in the context of harmonic oscillator?
Yeah. If you take harmonic oscillator, the fact that there is a harmonic oscillator is irrelevant. The algebra there, what is a basic algebra? The algebra there, the Hamiltonian is only giving you evolution.
Hamiltonian part of the algebra.
The Hamiltonian in the sister context, exponential IH is, exponential ITH is. Unitary is not H. H is not a bounded operator. The spectrum is not bounded. So it will not come here.
Basically, if I take the displacement operator in the base space, And if I take any linear combination of that will give rise to a bona fide operator.
Yes, that's it. So, the concept, by the way, the matrix analysis, prove it using matrices, this result for spectrum is not so trivial. It took me some time to get a generic proof, and it is given of all places by the book of Halmos. If you know this book of Halmos on matrices, finite dimensional vector spaces, it's a beautiful book, and it is some exercise buried in one chapter. So you have to go through that, Jordan decomposition, this, that, and you can finally prove it. Yeah.
So if I take a to the exponential minus IHT, what will be the norm of that?
One.
One.
Yeah, it is unitary. So they so this is an operator. So I told you take the maximum modulus of the eigenvalue. Exponential IHT is unitary. So
That will depend on P.
this modulus is one. That's all I need. So it's like living on a circle, no? The eigenvalues. The spectrum is living on. So how is it defined? How is this? May not be diagonalizable. Nobody says these operators are diagonal. So what? So if you look in books, they define something called spectral radius. Okay? So they don't want to use Hilbert space. So you take your operator A. Okay? It's in the algebra. Take any complex number lambda. Okay? And you ask, what is the maximum value of lambda in modulus? Okay? Find the maximum value of lambda in modulus so that it ceases to be invertible. So you are looking at what's it called? The Green's function. Okay? You look at when does the inverse, find the lambda where this inverse does not exist. That's a good way to take any operator in the algebra. Lambda is a complex number. Take the thing and see if I can find an inverse of this operator in the algebra. So can I find another operator, call it A prime of lambda, in the algebra? When I multiply it, I should get one. Find all these points, define points of the complex thing. These are the points where the Green's function is defined. Take the complement of that set. That is what is called the spectrum of this operator, original A minus lambda. In fact, you find the point where the lambda is maximum in the complex number. So where does it have maximum modulus? That is the norm of your original operator. So you don't need a Hilbert space or anything. It's defined intrinsically. Then you prove that it is unique. Okay. If there is this kind of a norm, it is unique. Otherwise, it doesn't exist. Okay. If you take an arbitrary algebra, say triangular, upper triangular matrices, okay, which comes in, say, SL2C. You take SL2C and take all the algebra with the upper triangular. They form they are closed under multiplication. Take the algebra. Does it have such a norm? No. So not every algebra admits this. Okay? It has to be a star algebra. Then you can start talking about this. So it can be intrinsically defined. Okay? You just take the spectral radius. That's the language they use. So I give you the prescription, which you can implement in finite dimension without any problem. Infinite dimension it's a different story. But it is the Green's function. It's coming from the Green's function. Okay. So what is the measurement problem? So here also, again, intrinsically in the algebra, I can define unitary operators. So I take any element of the algebra. So let me finish. Hamiltonian is not relevant. It is giving you how this algebra evolves in time. So there's a dynamical issue. It is relevant in quantum field theory and sneaks in through something they call the time slice axiom. But to define the algebra, it is not relevant. So what is algebra underlying harmonic oscillator? It is very bad. It is a set of all bounded operators on an infinite dimensional Hilbert space. It's huge. In some way, it is the simplest. They write B of H. In some ways, it is simplest. It is also what is called polynomial algebra. In some way, it is very simple. It is a trace. You can write density matrices. So it is called type 1 algebra. That's what we deal with in quantum mechanics. Hamiltonian tells you how, if you prepare this algebra in some spacious size or space-time volume, how it evolves. So that gives you what they call time slice axis. So we will hopefully come to that later. It has a very nice consequences. In particular, just to tempt you, there is a very important paper by Raphael Sorkin long ago, who presented an experiment in quantum field theory, where he showed an experimental arrangement which violates causality. In the relativistic quantum field theory, he presented an experimental arrangement which violates causality. But it's not a two-slit experiment. It's three successive measurements of three measurement apparatus. He arranged it in appropriate space-like directions. Okay. And he showed that in that arrangement, the standard axioms of quantum field theory show that there is causality violation. He showed it. This paper has been lying around for a long time until very recently it was proved, and the proof is not trivial, by Fuster. Yes, Fuster and Birch, and one of their colleagues, that if you use the axioms of algebraic quantum field theory and the causality requirements and the fact that you cannot localize states, Raphael's paradox does not apply. So it took something like 20 years to resolve that issue. That is a beautiful paper which all I can understand, all of us can understand, because it's quite straightforward. It only uses the standard double slit experiment type things, but a triple slit experiment. By the way, you may know that Raphael has written another paper with triple slits. He has generalized double slits to triple slits, in fact, to n slits. And he shows how the interference pattern changes for n slits. And for triple slit, an experiment has already been done in RRI by Urvashi. Yeah, who told that? Who said that? Urvashi? Yeah, you told that. Right? Yeah, I've seen that. It's very nice. Raphael was behind it, but it is a very beautiful experiment. They check. It's a sum rule that if you look at the pattern, and if you first close one slit, look at the pattern, it is. Then you close two slits, two at a time. Then you close all three slits. Raphael gave us some rule for all the three slits, and he generalized it to n slits and showed that it is actually cohomological destruction. There is a D of it, so a whole cohomology comes out. It's a very beautiful paper, and I was very impressed. I found it very beautiful, and just we check. So the same person has also published, not soon afterwards, causality violation in quantum field theory, and just got resolved it only very recently. Resolved, I don't know what Raphael says. He has not responded in public. Should ask him probably. So let me finish. Time is going up. Okay. So I want to tell what is the measurement problem, in my opinion, in quantum theory. The problem is that in quantum theory, I can write these unitaries, A plus A star, and U star is U inverse. Even if I do this Hilbert space construction, U will remain unitary. So star is like an adjoint. But this U no longer commutes it, and it is an element of the algebra, the observable algebra. So if I take the elements of the observable algebra and I take an arbitrary element in the observable algebra and I conjugate it with U, it will change. For example, if you take angular momentum algebra, take a rotation around third axis and conjugate it with an arbitrary operator, say rotation around an arbitrary axis, and conjugate it, it will change. So U inverse will not be B, it will change. But algebra will not change. The products will not change because these U's will start cancelling when you take products. So it is an inner automorphism of the algebra. The algebraic structure will not change. So if I do an experiment, I can change the meaning of individual operators by inner conjugations coming from unitaries in the algebra. And the non-commutative case, there are always these unitaries. I can change the identity of operators. Okay? So these are inner automorphisms. Now, if I tell somebody, so suppose now I want to measure angular momentum, and I give you a state and an algebra, but notice that the state I am taking may be such, state is coming from somewhere else. So I take B, some operated algebra, and I conjugate it. The answers I get can be quite different. I can show you states which change in value at B and UB universe. They can be quite different. So if I tell third party, measure third component of angular momentum, and that person does not have an external apparatus, and I just give the algebra of angular momentum, that person will not be able to measure it, because you would not know what is meant by third component. What is third component for the algebra? Algebra doesn't know anything like that. It is coming from some external system. For example, the lab frame. But there is lab frame is also quantum. So I should also describe it quantum mechanically. Then you have an infinite regression of unknowing as you keep going. You don't know what you're talking about. Okay? So, in my opinion, this is the problem of measurement in quantum theory, that you cannot measure individual operators in quantum theory because of this non-commutativity. There are a much stronger result of this kind due to Kohn and Stormer, who show much stronger results. Namely, they show that it is possible to do such conjugations so that you can reproduce the expectation value of any state on the algebra by these conjugations, so that the action of the unitaries, the inner automorphism from the algebra, is ergodic on the set of states. Ergodic, like you take a torus, a donut, something, and you go on winding around, never closing. It will become everywhere dense. Cornerstone shows that this happens in quantum theory. And they mention it, they say in the paper that therefore you cannot measure anything in quantum theory, and then they go off. They are involved in some other maths activity. So I think that this is the fundamental problem of measurement in quantum theory. And how is it resolved? I think Niels Bohr already had the correct idea. He talked about large quantum numbers, but I think he was talking about emergence of classical systems from large quantum numbers. So he was already imagining that from somehow classical systems are emerging in some fashion from quantum theory, but he was not very clear on what it is. He was talking about large quantum numbers. He did not talk about h bar going to 0. And this idea has been taken up by many people. In particular, there are people like Halverson, I think, Sivashish may know his name. Then Lansman, who is sitting in Nijmegen. He has written a whole book, or certainly articles on borification. And it is emerging now, and I should say, so I would say an emerging solution is that the commutative, it seems that a commutative algebra emerges from quantum theory in some what they call algebras living at infinity. The first person who proved in a quick, precise way this result is Klaus Hepp. Klaus Hepp has a paper long ago in the 70s where he discusses the lattice model, where using some research due to Ruel and somebody else, where in the StatMech contest, they have defined algebras living at infinity. The Hepp seems to have picked it up, but anyway, he constructed a specific StatMech model where you do get these algebras at infinity, which are commutative, so they are classical. Okay. So the algebras at infinity is what I call AC. They are commutative, and if you accept that for commutative algebras, measurement problems are solved, the data then is stored in this AC. Okay. So from AC is of course changing as evolution, for example, takes place in the interior. It is not autonomous; it is changing in time, and it should be codifying this data of what's happening in A. So the claim by Hepp and also I think Niels Bohr is that there is an underlying classical system, not by semi-classical expansion or anything, intrinsically from algebras at infinity, which are commutative algebras, and they code this information. that is the that is one line of development, I should say, which is evolving now. And this has also been noticed now that this kind of algebra emerges from super selection sectors in QED and QCD. You get a commutative algebra of super selected operators living at infinity, and they can also be caused by phase transitions. And this again was noticed by our friend Giorgio Mizzi, who has been here many times, and his colleague Fiorini, and also by Arthur Weigmann. Then it has been lying there, and now it is emerging in the recent works of algebraic quantum field theory. So I think this is an open system. I'll come to immediately. It's no sort of open problem. Sergio Doppler also has written a paper where he is trying to couple this commutative algebra to non-commutative algebra in some dynamical way, not by just. So the commutative algebra will be the somehow the measuring apparatus. Maybe. I'm not sure of the correct interpretation, but it's going in that direction. I would say this is an open problem, but the issue of measurement is not in collapse of, in my opinion, it is not in things like collapse of wave packets. It is something that is emerging from the non-commutative algebra and issues like causality. This is my opinion. Okay? This is my feeling, but we have to read. Yeah.
Imagine this algebra at infinity to pick what infinity are you talking about? Complex equation.
I'll come there.
Oh,
It's just that my theory is not what I would like it to be.
yeah. So the algebra that you mentioned, you're talking that there's this algebra at infinity which is complicated, right? So which infinity is it?
So, a quantized system with no boundary, I don't know how to. Yeah. Okay, let me say this. Okay. But I guess are non-convex cases. For example, that infinite lattice, that's origin versus infinite lattice. And Bohr's origin versus the large continental, like Rydberg atoms before. They are exactly. So you must be never exactly very large. And arguing that you get a content pattern. That this is the maximum model. And Giorgio and other way to do phase transition. So why phase transition? Paradigms. The spin direction of the movement can change. So the fluctuations may happen. So already super selection. Paradigm has super selection. Pinpoint 50 parts, there are nothing is simple. And if you want some operator to test it, that algebra one proves separately. You know, Giovanni has those people have proved it. That algebra is complicated. It's not good today. It's emerging now in quantum theory. And what we check that they are sensitive to local dynamics. And they say, what sensitivity, how do they read the data there and predict why Higgs is decaying? I don't know. I think these are all the problems. They have taken much more than 1 hour. So I stop here. Next thing will be probably not on 6, but I may not reach any time, but in the other 3, 6. Then I will go directly into the take a few minutes on what we have already talked about and go into the GNS conception. And I have to show you that things like partial treatment have no, I mean, again, no intensity. And so what goes wrong? And show also that quantum entropy is not unique. There are many systems where quantum entropy is not unique, even suppressed. But we know that the wrong thing. And show you how it happens. And go on to discuss things like thermal statements. So that will be much more convenient. In the next lecture, I come back to you. Algebraic.